So last time, so recall what's going on. I've got K, a finite extension of QP. And I was looking at L over K. Somehow I had to make some kind of design implementation decision. And somehow you could either deal with finite extensions or arbitrary extensions, arbitrary algebraic extensions. But what I'm really interested in is somehow arbitrary extensions such that which are only finitely unramified. I mean, I'm interested in some strange middle. Let's say L over K. Let's just say is algebraic normal and separable. And separable. Well, we don't need separable because we're in characteristic 0. So Galois. Then we can look at gal L over K, and we have this. Then we've got gal L over K. This now surjects into the Galois group of the residue field, KL over KK. There, and I need some name for the kernel of this map, which is the inertia subgroup. Let's define I L over K to be the kernel. There, so that's the inertia subgroup. Then I L over K is the inertia subgroup of this Galois group, gal L over K. And I'm going to spend a little bit of time saying something about the structure of this thing, because you see, this is the hard part, right? Because what have we got here? We've got some exact sequence. I L over K lives in gal L over K, and the quotient is this thing here, this Galois group of a finite field. So it's going to be gal KL over KK, and KK is finite, and so therefore this Galois group is easy, and therefore this Galois, gal KL over KK is procyclic, right? Is topologically generated by one element. Generated by one element. So maybe I should sell what I'm doing better. The idea is I want to understand what do I really want to do here. This is the basic object, this finite extension of QP, and what I'm really trying to do is I want to understand the absolute Galois group of this object. So I want to understand gal K bar over K. And I'm taking some kind of vaguely historical approach to how one's going to do that. So what I'm trying to do is I'm trying to get, so you could pretend that L is an algebraic closure of K. What I'm trying to do is I'm trying to understand this big, complicated, pro-finite topological group. And the first observation I'm going to make is that it surjects onto a group which is kind of rather easy. And the kernel of this map is this inertia group. So really what we have to do is understand this inertia group. Okay? So therefore, I mean, and there's also an issue in understanding an extension. But that's not going to be too hard. So we want to understand, to understand gal L over K, we somehow need to focus on this inertia subgroup. Need to focus on I over K. And as I say, I'm being a bit brave, kind of letting L over K be. Well, I think when I learned this stuff, in my head, L over K was always finite. And I don't think you're going to lose much by pretending that L over K is finite. Somehow most assertions I make, you can check them in the finite case. And sometimes you need finiteness because you have to do a counting argument. and then you carefully take some limit and everything's fine. So we better understand this inertia subgroup. So, and of course, I guess one thing we can observe is that this is a continuous map. This is a Hausdorff thing, so the identity is closed. So the kernel is the preimage of a closed set, so it's closed. So IL over K is definitely, what's clear is that this inertia subgroup, IL over K, is a closed subgroup of Galois over K. And so therefore, by fundamental theorem of Galois theory, corresponds to some sub-extension, which is going to be, I guess, the maximal unramified sub-extension. And so therefore, by the so therefore, by fundamental theorem of Galois theory, so IL over K corresponds to some M. L contains M contains K. And the way this is going to work is that this thing here, the Galois group here, is going to be the absolute Galois group of the residue field there, and the Galois group here is going to be IL over K there. So I mentioned this notation before. M is the maximum. There's lots and lots of extensions between L and K, and some of them are ramified and some of them are unramified, and M is somehow the union of all the unramified ones. So M is the union of all subfields of L containing K, which are unramified over K. So that's what's going on. Right. And I guess, one special case that we should perhaps do some of the universal case that ultimately we're going to be interested in is when L is K. Why am I constantly carrying this random extension L when really I'm only interested in L is K bar? That's going to become clear in about 2 minutes' time when I start talking about filtrations on this inertia group. So here's some special case, sort of special, interesting case, is when L equals K bar there. And then we have L, so here's the picture then. We've got K bar, and then we've got K down here, and then we've got this funny this extension here, which is the maximal unramified extension, so I'll call it KNR. And that goes up to K bar, and this has got Galois group I, K bar over K. And this has got Galois group, I guess, Z hat. Canonically Z hat. Because why is this canonically Z hat? Because because Gal KNR over K is canonically isomorphic to Gal, the residue field, algebraic closure of the residue field over the residue field. And I mentioned in the last lecture that this is a procyclic. So there we go. So what's this inertia group? Right. Oh, maybe I'll give you maybe I should also say that this maximal unramified extension is not so mysterious. You see, there's two things going on. When you do class field theory and you try to work out what class field theory says explicitly, there's two stories. There's kind of explicitly working out what the groups are and explicitly working out what the fields are. And they turn out to be two very different stories. Like for a random number field, we could look at somehow the maximal abelian extension of that number field, and we know exactly what the Galois group of that thing is by class field theory, but we don't actually know what the extension is. It's sort of funny. The machinery gives you the Galois group, but it doesn't say explicitly what the extension is. That's, even working out Hilbert class fields explicitly is kind of a serious issue in things like computational number theory. But anyway, what's this KNR? So here's an example. If K is just QP, then I think KNR is somehow the union of QP zeta m, actually a little m, there, with m an integer at least 1, and p doesn't divide m. If you start throwing in nth roots of unity, you're going to be careful. Like QP zeta p is ramified at p. That's kind of bad. But QP zeta m is unramified over. I think that's probably true. There we go. There's a live exercise generation. Is this true for, I think this is true for general K. I think that, yeah, I think this must be true. Anyway, we can worry about that later. So that's how we build unramified extensions. We could just, I mean, there's other ways of building them, of course, but here's an example. We can just throw in roots of unity, mth roots of unity for m prime to p. So now I need to talk about this inertia group, which is, of course, the hard part. And this is the kind of, I need to prepare, well, I have prepared, because this is slightly delicate. So, right, so now let's say we've got this extension L over K as usual. But let me assume the inertia group is finite, and assume that I L over K, oh, so I should say Galois, let me assume this inertia group is finite. Right, so in particular, if you're me at your age, then you were kind of slightly terrified of infinite Galois groups still. So you're just pretending that L over K is a finite extension, which is a perfectly reasonable situation to put yourself in. So e.g. L over K finite. Right, so what can we say about this Galois? You see, we're in this finite situation, so we've got this random inertia subgroup. I guess it's a normal subgroup because it's a kernel. We know that I L over K is a normal subgroup of Gal L over K. And we know that the quotient is, if L over K is finite, we even know that the quotient is a finite cyclic group. So need to understand this I L over K. So the first thing I'm going to do is I'm going to put a filtration on it. Let's put a filtration on I L over K. And we're going to, that's somehow, it's a good, if you've got some generally complicated mathematical object, if you can put a filtration on it, then we can look at the filtered pieces, and maybe that will teach us something about the object. So I need to explain how to put a filtration on this inertia group. To do that, we have to remember where the inertia group came from, right? These things are, if sigma is in I L over K, then sigma is in this Galois group, right? Then sigma is actually a map from L to L. And one can easily check that sigma sends the integers of L to the integers of L. And sigma sends the maximal ideal of L to the maximal ideal of the integers of L to the maximal ideal of the integers of L. And the idea is we can kind of ask ourselves how much disruption sigma does to these things here. So let's get this right. I guess the first thing we need to observe is that in this situation, because I L over K is finite, I claim that PL is principal. now. So let me because IL over k is finite, we actually know that we have that PL is principal. This came up in a question yesterday, right? If L was equal to k bar, then of course this thing is infinitely big, and L can contain like square roots of p, cube roots of p, nth roots of p for all p. And that was somehow an obstruction to making this principal. But what's happening here is because this inertia group is finite, you see we have L, and then we have M, and then we have K, and this is unramified, and this is IL over K. This is a finite thing, and the integers of M contain PM, and because this is unramified, that's still generated by a uniformizer down here, right? We have the integers of K, that contains the maximal ideal of K, and that's principal, because K is a finite extension of QP. Up here, it's still principal generated by the same thing, and up here we just have some finite extension, so it doesn't cause too much problems. I mean, up here, I should perhaps tell you that kind of VL curses. I'm telling you these things in a slightly strange order. Apologies. So the crucial point I need to make is that VL is on note, and VL goes from this discrete valuation satisfies kind of VL is the size of IL over K multiplied by VK on K star. So that's what's going on. The valuation only changes by some part. I'm just spending all this hard work. I mean, really, I only care about the case where L over K is finite. That's what's going on in my head anyway. And if L over K is finite, then L is a finite extension of QP, and there's nothing to worry about. Of course, this is principal. Perhaps I should have stuck to that case all along. Anyway, so PL is a principal generated by some uniformizer pi L, and we're going to look at what sigma does to pi L. That's the idea. So here we go then. If I is greater than or equal to 1, let's define I L over K little I. So here's my filtration to be exactly the sigma in I L over K, such that sigma of pi L divided by pi L. So all these things, all these elements of these Galois groups, they're all kind of continuous automorphisms, right? So sigma will send OL to OL, it'll send pi L to pi L, it'll send a generator of PL to a generator of PL. So sigma of pi L will still be a uniformizer of PL, and sigma of pi L divided by pi L, that's going to be a unit. So that's definitely going to be an OL star. And now the question is how close is it to 1? So I'm going to say this has to be in 1. This is sufficiently important, and I've left not quite enough space for it. So it's the elements in IL over K such that sigma of pi L divided by pi L is in 1 plus PL to the power. This is why I have to have my notes now, because I never quite know. This is I. There. So that's the filtration that we need to try and understand. So at the minute, it just looks like a random subset. But I guess it's not too difficult to check. There's probably a good way of thinking about it, isn't it? It's somehow I rather suspect that this is probably I L over k comma I is probably equal to the sigma, which acts as the identity on kind of OK mod PL to the I star. Anyway, so there's a definition. Right. Oh, and I should say also, it would be sometimes it's nice to talk about I L over k0. Let's set I L over k0 just to be I L over k. So there we are. And sometimes people even define 1 plus PL to the 0 to be OK OL star. That's a little bit, I don't know. Right. So there's some random definition. So now what we can check, not too hard. That these things are subgroups, right? It's that I L over k equals I L over k0, and that contains I L over k1, and that contains I L over k2, I L over k2, there. And these are all subgroups. Oh, curses, really? If I say I is 1, I want to get the pro-P, I want to get the Suloff subgroup. I'm telling you secrets, that's coming later. Do you think I've got that?
So I think you want them in the definition. Because right now, you plug in I equals 1 in the definitions, but automorphic sum is congruent, but acts as the identity line.
Yeah. The automorphisms. So this is definitely a unit. I'm still not understanding the problem.
No, yeah, maybe it's,
I think everything on the board is fine. Let's go carefully and let's see what happens, because I'm about to say more things about. Yeah. So let's check this. This is this. This lives in this. These are all subgroups. Are all subgroups of I L over k. Then they're all normal in G L over, and they're all normal in gal L over k. I L over k, comma I is a normal subgroup of gal L over k. And also, remember I L over k is finite, and if something in I L over k actually fixes pi L, then if sigma fixes pi L, then I think sigma must be the identity. Because it fixes M, I see, yes, because L is generated over M. Yeah, this is kind of handy, isn't it? L is M pi L. So if sigma fixes pi L, then it fixes all of L, so it must be the identity, because it fixes M. So furthermore, I've just shown that if sigma is not the identity, then it moves pi L. So sigma pi L over pi L won't be 1, so it won't be 1 mod PL to the I for I sufficiently large. So furthermore, if I is sufficiently large, then this inertia subgroup is going to be the trivial group. There. So we have a filtration on this inertia subgroup by more subgroups, and this is a finite filtration. Right. So now this is when we're going to unravel whether or not I've got things wrong. So as I say, the motivation for introducing this filtration is because I want to understand the quotients. And now here's the trick. So note next that this I L over k, if I quotient out by I L over k1, I'm going to write down a map from this. I'm going to embed this into KL star there. And that map is going to be sigma goes to, I need to come up with an element of KL star, and it's going to be sigma of pi L over pi L. Where's Jackie? Are you happy yet? You're happy. Wonderful. So there's some interesting thing. This is possibly infinite, remember, but this is a finite group, and a finite subgroup with the multiplicative group of a field is going to be cyclic, and furthermore, it's going to be cyclic of order prime to p. And in particular, the size of IL over k modulo IL over k1 is prime to p. Well, I can even say this entire group here is cyclic of order prime to p. So that's kind of nice, because remember we had the full Galois group, and then we realized that this was a cyclic part, the unramified part, and then this complicated inertia part, and we've just pulled another part of inertia off, and it's still relatively simple. Cyclic of order prime to p. But now, of course, the bad news is that I L over k, 1 can be a little bit more complicated. In some sense, the I L over k, 1 part is the real meat of this inertia group. But we can say something about it, because note also that if I is at least 1, then I L over k, I modulo I L over k I plus 1. So again, the sort of the general term in this filtration. So stuff in here, sigma pi L is 1. Sigma pi L over pi L is 1 mod PL to the I. Yeah, there's some issue. There's something we can do something with PL to the I over PL to the I plus 1, I think. So let's do this. So I'm going to map this into PL to the I over PL to the I plus 1. So maybe I should say this is isomorphic to kind of KL as a group under addition, as an abelian group. This is the additive group, because PL is principal. So this is non-canonically isomorphic to this. And the map here is sigma goes to sigma pi L over pi L. So sigma is in IL over k to the I, so that's in 1 plus PL to the I, so I'm simply going to take away 1. And that's in PL to the I. And if sigma is in this thing here, then this will be 0, because it will be in PL to the I plus 1. So there we go. So in particular, remember this is a possibly infinite, this is a finite group. I've now proved it's abelian, and it's a finite subgroup of this. This is a possibly infinite, this could be a finite field of characteristic P, or possibly infinite field, but as a vector space, it's a vector space over the field with P elements. And so this is some finite dimensional subspace. So in particular, this is this is now some finite dimensional vector space over the field with p elements, and in particular it has order of power of p. And in particular, this thing here, I L over k, I over I L over k, I plus 1, is isomorphic to z mod pz to some power, whatever ni. So it has order of power of p. There. It's also abelian, right? All these quotients have been abelian. This inertia group is kind of a random group. It's certainly not going to be abelian in general, but we've just written some filtration on it, and all the subquotients turn out to be abelian and relatively simple as well. So there's what we need about these inertia groups. Remember, I'm always assuming that these inertia groups are finite here. So these need to be checked. One needs to check that these are injective group homomorphisms, as I say, but these are not so hard, right? So these are relatively simple exercises. I think I did maybe put them on the example sheet. So these are... So, although we haven't completely worked out what this inertia group is, but one upshot is that I L over k 1, this has got order of power of p, and it's a normal subgroup, and the quotient has order prime to p, the normal subgroup of this inertia group. It's the unique Soulov p subgroup. Of I L over k. So there you go, and the quotient is cyclic. It's cyclic of order prime to p. There. So we're trying to understand this Galois group. Now let L be k bar. That doesn't make sense because these things aren't finite. But the idea is that somehow we should be able to take some kind of limit. And now this inertia group, we've pulled off some relatively simple bits, and what's left is a p group. In particular, it's solvable, right? So maybe I should say sort of, hence, in particular, this I L over k is a solvable group. Which was not obvious at the time. But I don't know. So, well, maybe I should say the extensions, there's a name for extensions of which I L over k1 is trivial. If we say that L over k is tamely ramified, if I L over k 1 is trivial. There. So this notation has a slightly funny consequence that somehow tamely ramified, it sounds like you're implying that you're ramified but that it's not too bad. And at some point in everyone's life, in fact, I've had several PhD students ask me independently, at some point in your life, you realize that you don't quite know if an unramified extension is tamely ramified, because somehow tamely ramified seems to imply a little bit ramified. So in some sense, the fault is with the notation. So note, maybe I should just flag this completely. Unramified extensions are tamely ramified. That's a trivial remark mathematically, This is more a linguistic note that tame doesn't imply it exists. So there we go. There's some tamely ramified extensions, and wild is the opposite of tame. So if I L over k, comma 1 is not trivial, we say L over k is wildly ramified. And wildly ramified certainly does imply ramified, right? So there's no linguistic issues there. So there's that. But as I say, what we're really interested in, so now there's a sort of slightly tedious technical thing. So we're really interested in the case kind of L equals k bar, because I'm trying to state the local Langlands conjectures, and these have got something to do with representations of gal k bar over k. But of course, none of the discussion above applies in this situation. But then I L over k is not finite here. So we have to work out how to glue everything together and take some kind of limit. And unfortunately, this lower numbering does not behave well with respect to extensions. So this lower numbering this lower numbering I L over k, comma I. It's called the lower numbering because the numbers that are appearing are subscripts. Does not behave well with respect to extensions of L. So I'll just leave that slightly informal, but what I'm trying to say is basically you change L to L primed, which is a bit bigger and ramified, then PL changes to PL primed and PIL changes to PIL primed. And your definition, this definition of this filtration, it involved what happened to PIL. So you make some ramified extension of L and then PIL changes completely. And all your numbering has kind of gone wrong. So somehow what I'm saying is that the image, I mean, I guess I could make a precise statement. Let me make a precise statement. If I've got L primed over L over K, and L primed over K is finite, and everything is Galois, so L primed over K and L over K Galois, and this thing here, then there's a natural map from IL primed over K that's going to surject onto IL over K. That's kind of easy. But unfortunately, I L primed over K, comma I doesn't get sent to, doesn't become identified with I L over K, I, via the natural map. So that's what happens in general, and like you do the calculation, you try to prove this is true, and you just get stuck, and the reason you get stuck is because it's not true. Because pi L primed is completely unrelated to pi L, basically. And so you're trying to, I've lost the definition, but you're trying to control things modulo PL to the I, but this is a question about PL prime to the I, which has nothing to do with PL to the I. I mean, it's to do with PL to the kind of I times E or something, where E is the amount that this is. You see there's some scaling issue. This will be something to do with I L over K of I times E. That'll be what's going on. So this is kind of fixed in a rather beautiful way. So there's a fix. There's a rather crazy fix. We introduce a new somehow relabeling of the filtration. Of the filtration. And I'll spare you the details, but here's the idea. So let's have back to, so forget about L primed, we've got L over K Galois, and we'll have I L over K finite, as before. And what I'm going to do is I just need to introduce some numbers. I'm not going to prove the big theorem. As I say, the proof is rather fiddly in Sayre's book on local fields, for example. So let me define let me say GI is the size of I L over K, comma I. So GI is some random integer. So I guess G0 is at least G1 is at least kind of whatever. G capital M is 1 for some sufficiently large n. So there's GI, and now let me define completely out in the blue, and let me define, this map is traditionally called phi, from the non-negative reals to the non-negative reals. And it's some slightly ridiculous definition. It's going to be piecewise linear. And it's going to have possible breakpoints at integers. So phi is piecewise linear. There. And so I guess with breaks, I mean, so somehow, in fact, phi is linear on all kind of intervals I, comma I plus 1. Oh, so it's piecewise linear and continuous. There. Phi is linear on I, comma I plus 1. So the graph of phi looks like this. It's going to, that's what it's. So phi of 0 is 0. And the last thing I need to tell you is what the slope is on I, comma I plus 1. So phi is just supposed to be some decent scaling factor. And again, I've got to be note bound to make sure I get this right. So and on I comma I plus 1, phi has a slope G I plus 1 over G0. So there we go. So the GIs are getting smaller. G0 might be big. G0 is the size of the full inertia group. Then these i's get smaller and smaller and smaller. And so this picture I drew here is kind of fairly accurate, at least. You start off with the biggest slope, and then the slopes get smaller. I mean, maybe I'll say, so maybe I'll give somehow an even better picture. You start off with slope G1 over G0, and then you get G2 over G0, G3 over G0, and eventually at some point all the GIs become 1, and so you get slope 1 over G0 there. So eventually this is slope 1 over G0 if U is very, very large. So that's what phi looks like. So it's easy to check that phi is an increasing bijection, right? So phi 0 infinity to 0 infinity is an increasing bijection, strictly increasing bijection. And we're just going to use phi to kind of rescale the filtration. Okay? So let's define if V is in the reals, V is at least 0, let me define the lower numbering I L over K, comma V. So remember, we've defined this for V an integer, but let me just define I L over K V to be I L over K, the ceiling of V. So now my filtration, it used to be, I used to have a filtration that was defined on every integer, and now I've got a filtration which is defined on every real number. But of course, it's not really anything new. So here V means it's the smallest integer, I, which is greater than V. There's my definition of ceiling of V. So now I have a lower numbering indexed by the real numbers, and so now finally get the upper numbering. So definition is the upper numbering. Let me define I. So here we've got U is in the real numbers at least 0. I L over K, U with the upper numbering is by definition I L over K, some lower numbering thing, and it's phi inverse of U. There we go. So there's some kind of linear rescaling, and now if you grit your teeth and do the calculation, it turns out that this filtration is well behaved when you start changing. You replace L by L primed, and the lower numbering starts jumping around, but also, of course, all these GIs start jumping around as well. And the point about phi is it kind of controls the jumping precisely. So the proposition that I won't prove, so proof in, I think it's in Serre local fields, or maybe Cassels-Fröhlich. Is that this new renormalized upper numbering, if L primed over L over K, these are all Galois as usual. Extensions are all Galois, and IL primed over K is finite. So we're in the situation we've been talking about. Then this upper numbering is good. Then I L over K, U, upper U, is exactly the image of I L primed over K, upper U, via the obvious map. Proof omitted. Apparently Cassels and Fröhlich, page 38, apparently. If L primed over K is finite. So there we go. So that's how, maybe I should say, where did I do it? So I defined this here. So I've got my filtration, which is defined, it jumps, it's defined on the integers, and then I've defined this filtration here. I've let V be a real number. And so now if you kind of look at the graph of IL over KV, then the graph jumps, right? So somehow the size, maybe I should draw. So here's a graph of V goes to the size of I L over K V with the lower numbering. The graph kind of looks like this. Here we get G0, and then the moment we leave, it goes like this there to G1. Now here's 1, and then that lives there, and then that lives there. So I'm trying to indicate the continuity somehow. This I L over K1 is really I L over K1 minus epsilon, but it's not I L over K1 plus epsilon. There. So you see, this graph jumps. at random v's in the integers. And so when we use the upper numbering as well, so what about the graph? The graph of u goes to I L over k upper numbering u. So this is going to have jumps as well because it's just some rescaling has jumps. But because I've done this weird rescaling, like with kind of random slopes here, like 1 over g0, with g0 some random size of some group, these slopes, these jumps might not be at integers anymore. Jumps may not be in z. But if you think about it, they are going to be in q. There. And in fact, you can do even more. Right? You can say even better because the slope is always some whole number divided by g0. So I guess the denominators of where the jumps are will divide g0. So there we go. So the point of all this is that with the upper numbering, these things glue together very well. And so for the upper numbering, this upper numbering will extend to an infinite extension. So while I'm here, let me tell you, although I don't think we're going to need it, let me tell you the Hasse-Arf theorem. It's kind of a crazy theorem of crazy name, crazy theorem. Here's a random thing just for your, I don't think we're going to need it, but for your edification. If L over k is abelian, then the jumps in the upper numbering are also at integers. Then the jumps in the upper numbering, I, L over k, u, are always integers. I have no real understanding about why that's true. Well, I mean, it's just some random fact. So for a random extension, these jumps will be at random rational numbers. But if the extension is abelian, then the jumps are always at integers. As I say, this is in contrast to the lower numbering, where the jumps are always at integers just by definition. So there's Hasse-Arf. And so now, of course, let's glue everything together. And so finally, we can talk about L equals k bar, now if any. So now if L is, if L over k now is any Galois extension, there we can define, so I L over k u there by gluing together, by gluing I m over k u for m over k, whatever, algebraic, and I m over k finite. So there. So now we have a filtration on this inertia group that makes sense even in the infinite case. So there you go, and that's kind of all we can say about that filtration, really. But it's somehow it's a useful tool. Right, let's get back to how are we doing for time? When did I start? I speak till 10:45, right? Yeah, great. You kids have probably not really ever given too many lectures. But I must say that it is an absolute luxury being able to speak for 2.5 hours every day, because you always feel that you have a lot to say, but somehow you have so much time to say it. How are you doing? Oh, I'm just going to start going about something else now. Any questions? That's what you're supposed to say in America, right? Americans say that all the time. No, they're real numbers now, right? Yeah, this is a kind of a using the real, but they only jump at rational numbers. It's quite difficult to draw functions which are somehow. Yeah. I once asked John Coates if this function was somehow continuous at every irrational and jumped at every rational, and he was like, "Oh, I think so." And he somehow went to his office, and he came back with somehow a handwritten letter from Tate where he'd sketched some argument. And Coates had kept it, which is indeed the case. I can't remember how. If Tate did it, it's probably tricky. So it might be a very hard exercise to check that for a random rational number u, you can find some L over k for which the thing jumps at u. Anyway. So now we don't need it now, right? So here, if I m over k is finite, then I've defined this. I've now just defined this, right? I'm going to define that to be, that it's going to be the stuff in IL over k that lands in IM over ku for some appropriately chosen m. Yeah, I guess for all m, that's the point. Right, so recall I defined L over k to be tamely ramified if so this was when IL over k finite. I defined tamely ramified if IL over k 1 was trivial. Okay, but now we've done this crazy introducing a real number. This is equivalent to, of course, this is kind of equivalent to IL over k, comma epsilon is trivial for all epsilon bigger than 0. You see, it means that you have some interesting inertia group, but then the moment you move away from 0, it becomes trivial. You see, and of course this is equivalent to IL over k delta equals 1 for all delta bigger than 0. And of course this now makes sense for arbitrary extensions. And this last definition is good for any Galois L over k. There. I mean, you can even define what it means for a not Galois extension to be tame, but I'm not so interested. So same story, tame extension. If compositum of two tame extensions is tame. Of two tame extensions is tame. There, and now we have the language. So therefore, we can talk about maximal tame extensions. Therefore, L over k contains a maximal, just like it contained a maximal unramified extension, it contains a maximal tamely ramified extension. There. Yeah, why not? That works. That works for me. So I guess for a general, so now here's our general picture then. So L over k is Galois, there's L, and there's k, and there's something here. Somehow there's some kind of k1, and this is maximal unramified extension, and now there's some k2 here, and this is the maximal tamely ramified extension. Maximal tamely ramified extension. I've written this picture and I've realized actually it's a nice picture about which I want to say more. So let me just write it again. There's L, here's K2, here's K1, and here's K right down the bottom. There. So this is unramified. and this is tamely ramified. And this is the wild part. So wild. This is wildly ramified. And in this generality now, because L is a random extension, L can now be K bar, because I've done all this work with this phi. L can now be K bar, and so this can be some huge infinite extension. But the Galois group will be pro P. There. I mean, in the finite case, it will be a finite P group, and in the infinite case, it will be a projective limit of finite P groups. So if you know about pro P groups, there's still some good theory of, there's Sulov's theorems and stuff like this. There's orders, and somehow this just says the order of this is P to the power infinity, as it were. And this we understand. This Galois group is cyclic, and this one here we also saw in the cases when L over K was finite. This Galois group was cyclic of order prime to P. So we have a cyclic extension, a cyclic extension, a pro P extension. So that's what the absolute Galois group of K looks like from this point of view. Let me say more about why this tame extension. Let me explicitly tell you what this maximal tamely ramified extension is. It's not so difficult. Well, let me do the case. Let me do the case of K bar. So we've got K bar, and here we have KT, and here KNR, and here's K. There. So this is the maximal tamely ramified extension. So how is this going to work? Well, so what is KT, right? That's just... so I can tell you what it is. So let's go back to, if L over K is finite in Galois, then we saw, and we have this picture, L, there. So now I'm going to go back to K2, K1, K. And this extension here, this had Galois group I L over K modulo I L over K1. And this turned out to be, this was cyclic of order prime to P, M, if P doesn't divide M. There. So this Galois group here is cyclic of order prime to P, and in particular, it's cyclic. And there's something called Kummer theory, which I learnt about in Birch's article. I found Cassels-Fröhlich quite an intimidating book when I was your age, but my entry point into that book was somehow Birch's article. Because I'd done a course in Galois theory, and I found that really Birch was only really doing... my commutative algebra wasn't, so I was still a bit terrified by kind of Dedekind domains and stuff like this, but my Galois theory was solid. And I read Birch's article in Cassels-Fröhlich, and it taught me a lot. And one of the things it taught me was, in some cases, you can really write down all the cyclic extensions of order prime to... you can write down the cyclic extensions of order M of some field as long as the field contains the mth roots of unity. So now Birch, so maybe I should say, so by Kummer theory, so see Birch's article in Cassels-Fröhlich. So Kummer theory says something about cyclic extensions. So note that this KNR, right, KNR is going to contain all the mth roots of 1, right? The mth roots of 1, group of mth roots of unity. In K bar. And that's because P doesn't divide M. So throwing in an mth root of unity, we get something unramified. You see. So actually, so if kind of K2 over KNR is Galois with Galois group cyclic of order m, Z modulo mz, with Galois group isomorphic to a cyclic group of order m, then by Kummer theory, we must have obtained this extension by taking an mth root of something. Then K2 must be kind of KNR as an mth root of alpha for some alpha in KNR. So that's what Kummer theory tells you. The way you get cyclic extensions is by throwing in mth roots. There. It's not too tricky. It's not too hard to check. But in fact, the only K2 must be I mean, in general, if I take like the rational numbers certainly contains all the square roots of unity. Where's my? Oh, yeah. So the rational numbers contains all the square roots of unity, plus or minus 1. And so the degree 2 extensions of the rational numbers are what I get by taking a square root of something, like q root n, q root p. These are quadratic extensions of q with Galois group cyclic of order 2. But there's lots and lots of different ones. Here we're in some situation where we've taken the maximal unramified extension of some field where there was only one prime anyway, and it turns out that somehow we've unraveled everything, and there's only one we can only take the mth root of one thing, basically. K2 must actually be KNR, mth root of pi k. There. This isn't so difficult to prove. Like alpha is pi k to the some power times a unit, and mth roots of units give you unramified extensions. So we must have taken the mth root of some power of pi k, and then by just mucking around, you can convince yourself that we've taken the mth root of pi k. And so now, putting this together, we can so can conclude, can check now that this tamely ramified extension, this KT, is actually must be KNR, the union for m at least 1, p prime to m, is going to be the union of KNR mth roots of pi k. So that's what the maximal tamely ramified extension looks like. So the unramified extension, we've taken all the mth roots of unity for m prime to p, and then the tamely ramified extension, we're basically taking the mth roots of p. If k was equal to qp, I'm just taking the mth roots of p for all m prime to p. So there's what that tamely ramified extension looks like. And in particular, I can work out what the Galois group is. And well, maybe I should work out this note that this gal KNR, take an mth root of pi k. What's this Galois group here over KNR? But it's cyclic of order m, and then here's a way to see it's cyclic of order m. It's actually isomorphic. It's canonically isomorphic to the mth roots of unity via the map. Sending sigma in the Galois group goes to, you see pi k, that's in the base field, so Galois doesn't move pi k, but of course it can take an mth root of pi k and send it to a random different mth root of pi k. So if I look at sigma of the mth root of pi k, and I divide it by the mth root of pi k, that's going to be a root of unity. So it turns out this is a group homomorphism and this is an isomorphism. So this Galois group is actually canonically isomorphic to the mth roots of unity. I suppose while I'm here, I could even, so in fact now we've now got some kind of non-canonical isomorphism. It's nice to have canonical isomorphisms because you can write them as equals and somehow you know that all your diagrams will commute. But let me temporarily let me temporarily write down a non-canonical isomorphism. You see the problem is in this issue I've got m nth roots of unity. This mu m, the group of mth roots of unity, is certainly cyclic, but I haven't got a canonical generator. Right? If this was the mth roots of unity in the complex numbers, I could kind of take e to the 2 pi I over m. You know, if you really put a gun to my head and demanded I choose a generator of the mth roots of unity in the complexes, I could choose e to the 2 pi I over m. But in some random field like an algebraic closure of the periodic numbers, I don't really know how to choose a canonical generator. So what can we have here? And so hence, so in particular, so this gal kt over kr, knr, oh, they were up here. This is equal to the projective limit of these mu m's there. So this would be kind of non-canonically isomorphic to the projective limit of z mod mz's there. And so this would be, so remember this is all p doesn't divide m, right? So this thing here would equal, I guess, the product for L not p, ZL. So this is non-canonical, right? So here's our picture. What we've done today, rather rapidly, but we're somehow there. So here K is my finite extension of QP, and here we have a maximal unramified extension and a maximal tably ramified extension, and then the algebraic closure up here. This is a pro-P group there. This Galois group is non-canonically isomorphic to the product for L not P, ZL. And this Galois group is canonically isomorphic to Z hat, which is the product for L, or the product for all L, ZL. There. And if you'd really rather play with finite extensions, then take a finite Galois extension. You see, this is just, infinite extensions terrified me when I was your age, but somehow this is just packaging of, this is just clever packaging of data about finite extensions. What this says is if I've got a finite Galois extension of p-adic fields, then there's a maximal unramified extension, and the Galois group is cyclic with a canonical generator. And then there's a maximal tably ramified extension, and the Galois group here will be isomorphic to a cyclic group, but with no canonical generator. And then we have a finite P group at the top, right? So I'm making that assertion for all finite extensions at once, and I'm cleverly packaging everything together, which gives you this very fancy-looking infinite Galois theory story. But all I'm doing really is taking some direct limit. So you shouldn't really be. I mean, not only that, but every time I prove something, I reduce to some finite case, and then you do everything for the finite case, and then you take some limit. So it shouldn't really be that scary. So if I'm trying to understand, if I'm trying to understand this big group here, then it would somehow. This pro-P group is non-abelian and difficult in general, but at the very least, I should know, it would be nice to here's a group we haven't really quite understood yet. It would be nice to understand that group there, the Galois group of the maximal tame extension. And the reason we haven't quite understood it is because we've isolated a normal subgroup that's cyclic, and we've got a quotient that's cyclic. But if you just have some random group with a cyclic subgroup and a cyclic quotient, that you have to figure out what the glue is, right? This is going to be a semi-direct product, but to make it a semi-direct product, I need to say how this group acts on this group. So maybe I'll say, maybe I can look at my notes and say what I was supposed to be saying next. But yeah, so okay, well, I don't care. I'm going to say this. I'm going to say this anyway. So I guess this is exercise. We can now understand gal kt over k. As I say, we haven't quite, by understand, I mean we can really explicitly nail it now. We can write it down. We have a subgroup which is cyclic and a quotient which is cyclic, but we need to say, so we have a pro-cyclic sub and a pro-cyclic quotient, And this procyclic quotient is generated by some canonical generator, right? A canonical generator. So this generator needs a name. It's going to be called frob. So what is this frob? How do I know that this group is cyclic? It's because it's the absolute Galois group of some finite field. So let's just remind you of this here. My Galois group here, I've got gal k n r over k. This is canonically isomorphic to gal, I guess, this Galois group with the residue fields, and this contains the map x goes to x to the power q. That's the generator of that Galois group. If this is infinite, this is a topological generator. So q is the size of the residue field. So that is a canonical generator of this group, and that generator there corresponds to some element in this Galois group here, and this is going to be called frob. Okay, that's the definition. So we've got frob, this Frobenius element, in here. Frobenius would somehow turn in his grave if he saw all this stuff, I would imagine. So there's the Frobenius, but on the other hand, he'd probably be pleased that his name's gone down in history. So there's our generator, and the question is basically, I want to see how frob. You've got to be careful, right? Frob is not an element of gal k bar over k. Frob is an element of gal k nr over k. Okay? So now we have to understand, so this is some exercise in finite group theory. Again, I remember when I was your age, I was very unclear about how groups glued together. I knew there was something called a semi-direct product, but I didn't really have a good understanding as to what extent that was the answer. But now I'll just tell you. You can go ahead and figure it out yourselves. We've got this group here, and we've got this group here, and we want to know this group here. So what extra piece of data do we need to figure out to give us that glue? Well, we're in a good situation here because this is cyclic and this is abelian. So we can lift frob. If we lift frob to gal k tame over k, there, then so now it's an element of the group that we're trying to understand. Then, of course, then it acts by conjugation. On the normal subgroup, gal kt over knr, right? So this just goes to x, whatever, or sigma is probably a good name for it. Sigma goes to frob, sigma, frob inverse. And so the point is, this is independent of the choice of lifting, because if I have another lifting, then it will be frob times an element of this abelian group, and the element of the abelian group will commute with sigma. So to say what this group is, we have to say what this action is. That's the missing piece of information for saying what gal kt over k is. And I told you that this group was non-canonically isomorphic to this thing here, but it's canonically isomorphic to so gal kt over knr is actually canonically isomorphic to this limit over m of mu m from k bar, right? And so we have to figure out. So this is a group. And we've just given a map from this group we've given a group homomorphism from this group to itself. There's actually an isomorphism, of course, because we can just conjugate by frob inverse to get back to where we start. So the missing piece of data is an isomorphism from this group to itself. So the exercise is check that frob, check that the map induced by frob by Frob is actually the obvious Frobenius. Remember where Frob comes from on the residue field, it's x goes to x to the power q. And it turns out that that's exactly, you see, this is the reason I've written it this way now, this is a canonical isomorphism. And so all the diagrams you should ever write down are going to commute, you see. And so we have to now guess how Frobenius is going to act on a group which is canonically this. And Frobenius is something to do with x goes to x to the q. And x goes to x to the q makes sense here, because q is a power of p and m's prime to p. So you check the map induced by Frob is simply the map zeta goes to zeta to the power q. You see. So there's the glue. So this is the glue. Which telling us what this Galois group is, what gal kt over k is, kt over k. So there you go. So there's the answer. I don't think we're really going to. I mean, this is just some parenthetical remark in some sense. You know, what I'm saying is, just because we know that this is cyclic and this is cyclic, it doesn't quite tell us what there's still some lemma to be checked before we actually know what this group is. But there we go. So now we've got this group here, which is a big semi-direct product of a cyclic group by a cyclic group, and then we've got this funny pro-p group, about which I said essentially nothing. Oh, and I'm even over time. I'm really sorry. It's a good place to stop, but it's a bad place to stop in terms of being 7 minutes late. So we'll break for 15. So I'll start 7 minutes late for the next one. So next is going to be statements of local class field theory, just to let you know.